Practice problems. Unitary matrix examples. So here are some examples of unitary matrices. So notice this is complex, and so notice it's also Hermitian. Here is a non-symmetric, non-Hermitian, complex unitary matrix. So again, unitary matrices, when you multiply it by its adjoint, you get the identity matrix. So its adjoint is its inverse. Okay. Orthogonal matrices, on the other hand, are real matrices. So these are properties of orthogonal matrices. For normal matrices, here's an example of a normal matrix. It's an identity. So this matrix is normal. That is, A adjoint A is equal to A adjoint. This matrix is unitary and orthogonal. That is, since A adjoint A is the identity, it's unitary. Since it is real, it is orthogonal. So remember, since a normal matrix has a unitary matrix that makes it diagonal, the unitary matrix in our case that makes this diagonal is A itself, the identity. That is, the unitary matrix is the original matrix in this case. This matrix is Hermitian and symmetric. So it is self-adjoint and symmetric. And the matrix is positive definite. So there's a lot of stuff going for this identity matrix. Here's a Jordan matrix. Okay, so we can see an example of a Jordan matrix. What about a positive definite matrix? One of the properties of a positive definite matrix is that all the principal minors of the matrix must be positive. So I look at a matrix like this, it's got some negative numbers in there. How can it be a positive definite matrix if it has negative numbers in it? Well, a positive definite matrix can have negative numbers in it. It's just that the negative numbers need to be in some certain places. So the principal minors must all be positive. So in particular, we must have the determinant being positive. Okay, because the determinant is the largest principal minor of the matrix. But the other principal minors are all submatrices along the diagonal, and those must have positive determinant. So if we go through and we look at all the principal minors and compute their determinants, we see that they should all be positive for a positive definite matrix. Okay, so we can go through and see all of those different principal minors. That was cool. Let's look at it again. So here's the 2 by 2, the next 2 by 2, the next 2 by 2, now 3 by 3s. Okay, so we've gone through and looked at all 2 by 2, 3 by 3s, and also if you look at the diagonal elements, those are the 1 by 1s, and you can see those must also be positive. So if all the principal minors are positive, then the matrix is positive definite. Okay. So again, another way of looking at a matrix to see if it's positive definite is to check the eigenvalues. If all the eigenvalues are positive, then the matrix is positive definite. Now here's some examples of positive semi-definite matrices. So here's a positive semi-definite matrix. Here is a positive semi-definite matrix. What about this guy? What about that guy? Is he positive semi-definite or not? It looks very similar to this guy. Well, here are some other properties of positive semi-definite matrices. If either of the multiplied in either of these two, this matrix is positive semi-definite. This matrix is positive semi-definite. It may be positive definite, but anytime you take a matrix and multiply it by its adjoint, you'll get something that's positive semi-definite. So we're going to have that a lot. In fact, this matrix here is this column multiplied by this row. It's a dyad, and we get a positive semi-definite matrix if we look at it from this way. So if A is that first column and A adjoint then is that first row, then this matrix is this, and so it's positive semi-definite. Now it turns out that for a matrix to be positive or positive semi-definite, positive definite, the diagonal elements need to be non-negative for a positive semi-definite, and the determinants, again, of the principal minors must all be positive. So if I look at the determinant of this matrix, that's 1 minus 4, which is minus 3. So that principal minor has a negative determinant, and that means that this matrix is not positive semi-definite. So even though it looks similar to this matrix, it's not. And so what ends up happening is you have something called diagonal dominance. That is, the diagonal elements for a positive semi-definite matrix generally need to be larger than the off-diagonal elements. So notice here, these diagonal elements are larger than the off-diagonal elements. And so you can go through and show that this is a positive semi-definite matrix, whereas this one is not. Okay. Again, you can also go through and check by computing the eigenvalues of that matrix and checking them. Again, a dyad is a matrix when I have a column times a row, and so this is an example of a dyad that we get. So those are examples of those special matrices. So with matrix decompositions, so this matrix A we can go through and show is equal to V, AV is equal to VJ, where V is this and J is that. So I have a Jordan decomposition here. I haven't shown you how to get that Jordan decomposition, but this is a Jordan decomposition. So this is an example of one. Singular value decomposition. If I go through and do the SVD on this, here's my U, here's my S, and here's my V. Notice that we will often get square roots of things coming out when we do the singular value decomposition. So we'll often get square roots of things. So this is an example of a singular value decomposition. This matrix has this singular value decomposition. So again, notice that I have sigma, which is the diagonal block. In this case, this has repeated singular values, which is, so that's the largest singular values. And then I have zeros. So I have a diagonal as far as I can go diagonally. Okay, so even a non-square matrix can have singular values. All right, how do we compute the singular value decomposition for a matrix? So let's look at this matrix here. When we multiply A transpose A, this is what we get. When we multiply A transpose, this is what we get. And now we need to compute the eigenvalues or the eigenvectors of these two matrices. So when we go through, we can compute for this matrix the eigenvectors. And in this case, because the matrix is square, S actually comes out in the middle of this, actually S squared. And so this set of vectors is going to give us, so if I multiply this out, the eigenvector decomposition gives us these vectors, and the eigenvector matrix ends up being a matrix of the singular values squared. So we call it S squared. Okay, so that's A transpose A. When we do A transpose now, we get the U coming out. So that's how we compute the U. And so we can go through and show that that the U and the V are both orthogonal matrices, and so S is the square root of S squared, and so this is the singular value matrix, and we have our U and our V given. So we have that relationship. Again, with singular values, we have Schmidt pairs, and again, graphically, a matrix maps a circle into an ellipse. If it is in 3 dimensions, then it would be a sphere gets mapped onto an ellipsoid, and so forth. All right, matrix decompositions. Again, we have this MATLAB code that we can use, LR, LU, QR. So we have these different things that we can use. So let me now take some time to actually go through MATLAB and to look at some of these things.